Look at these two inequalities. If you're staring at a screen full of variables, negative slopes, and large numbers, your first instinct might be to skip it. Systems of inequalities are designed to look overwhelming on a test, but you don't need a graphing calculator or a ruler to solve this. We can break this down using a straightforward algebraic strategy that takes under 2 minutes. First, we need to isolate exactly what the exam wants from us. Right here, the prompt is asking for the maximum possible value of b. Test makers love to throw in unfamiliar variables to create confusion. When they ask about a point with coordinates a and b, that is just a coded way of talking about standard x and y coordinates. A is x and b is y. So our only real objective is to find the absolute highest y value allowed by these rules. To figure out where that maximum point lives, we first need to picture the boundaries. Since both of our inequalities use less than or equal to symbols, we are looking for the physical space on a graph that sits underneath both lines at the same time. Let's visualize the first line. Y is less than or equal to negative 15x plus 3,000. It's a steep, downward-sloping boundary, and any valid solution has to fall somewhere in the shaded area below it. Now we drop in the second boundary. Y is less than or equal to 5x. This one slopes upward, and just like before, its solutions fall into the area below. The actual solution set for the system only exists right here, in this overlapping wedge where both conditions are true simultaneously. Every single point inside that wedge is technically a valid solution. But remember our goal. Where is the absolute highest y value? Looking at the shape, the peak is obvious. The highest vertical point is exactly where the two lines cross. This gives us our core rule for grid-in questions. Because the highest value is restricted by these intersecting boundaries, the maximum must be the point of intersection itself. We don't have to draw a perfect graph. We just need to calculate that exact crossing point. To find out exactly where these lines cross without graphing them, we use the substitution method. We simply set the two equations equal to each other. Since both equations are already solved for y, we can take the 5x from the second equation and plug it directly into the y spot of the first equation. That gives us 5x equals negative 15x plus 3,000. Now we do the algebra to isolate x. We add 15x to both sides to group our variables together, leaving us with 20x equals 3,000. Divide both sides by 20, and we find that x equals 150. Stop right there. If you bubble in 150 as your final answer, you will lose the points. This is the single most common trap on the test. 150 is our x-coordinate. In the context of the problem, that is variable a. But the question didn't ask for a. It demanded the maximum value of b, which means we need the y-coordinate. To find y, we have one final step. We take our newly discovered x value and plug it back into either of our original equations. You can choose either equation, but tactically, you should always pick the simpler one. It minimizes the chance of making a careless arithmetic mistake under pressure. The second equation, y equals 5x, is much cleaner. So we drop our x value of 150 right into that spot. 5 times 150 gives us 750. By skipping the physical graph and relying on substitution, we've pinned down the exact coordinates of that intersection. We've proven the highest possible y value is 750, with 0 guesswork. Checking this against our source material verifies the calculation. 750 is the correct answer. Let's review the framework. First, when a question asks for a maximum value within less than or equal to boundaries, you are looking for the literal peak of the solution set, the intersection point. Second, you extract that intersection point mathematically by using substitution, setting the two equations equal to each other. And third, guard against the trap. Always double-check your variables before locking in a number to make sure you didn't just solve for x when they specifically asked for y. Once you practice this 3-step process, intersect, substitute, verify, these problems go from overwhelming to completely manageable. Try applying this exact framework to the practice questions linked below to secure those points on test day.